Good afternoon, everyone. My name is Tsvetan Burticelov, and I will present some initial results on the individual elements of a local oscillator for use in atomic clocks. I will start by giving a simple, basic block diagram of an atomic clock. It has the local oscillator, the frequency synthesis chain, the physics package, and the phase detection and feedback electronics. And one of the main limiting factors in the performance of an atomic clock is the phase noise of the local oscillator. And this is where this talk is focused. Now, initially, when we started working on the local oscillator, we envisioned a system which would have three different oscillators: a 10 megahertz crystal oscillator, a 100 megahertz crystal oscillator, and a 1.5 gigahertz DRO, all phase locked together so we can get the optimal phase noise from all of them. But when we compared the performance of the DROs that we could build at York with some of the very best 100 megahertz and 120 megahertz crystal oscillators available, we found that our DROs can achieve better phase noise performance at all offsets than the multiplied up phase noise of those oscillators. So in the end, we decided to exclude the 100 meg crystal oscillator from our synthesis chain and only use the 10 megahertz and 1.5 gigahertz oscillators. Then we could possibly use a DDS, which could be clocked by dividing down the frequency from the DRO. That would produce a 17.8 megahertz signal, which we can tune and modulate directly from the DDS. Then we can offset the 1.5 gigahertz frequency using a single sideband mixer, and that will produce the frequency to interrogate the rubidium-85 resonance. So that means that the key elements of the local oscillator are the 10 megahertz crystal oscillator and the 1.5 gigahertz DRO. The 10 meg oscillator would offer a very good close to carrier phase noise, while the DRO would offer a very good medium offset phase noise and very good noise floor. And by phase locking them together, we can get the best from both worlds and get the optimal phase noise at all offsets. Now, how were these oscillators designed? The theoretical model that was used was developed by Professor Everard and is described in his book and was presented also at the previous conference. It uses, the diagram is pretty basic. It has an amplifier with two distinct inputs. One is dedicated to the noise and one to the feedback path. And the resonator is represented by the RLC equivalent circuit model. Now, using this model, we can express the phase noise of the oscillator as a function of the ratio of the loaded to unloaded Q. And it was found that for the optimal phase noise, the ratio of loaded to unloaded Q has to be about half. And this means that the insertion loss in the resonator will be 6 dB. And in this graph, we can also see that if the insertion loss in the resonator is within the range of 3.5 to about 9.5 dB, the phase noise degradation is lower than 1 dB. Now, for the 10 megahertz crystal oscillators, they were built using the feedback oscillator topology. The sustaining stage is a differential amplifier. Then we have a spurious resonance rejection filter, which is used to filter out the 10.9 megahertz unwanted resonance in the crystal. We have an electronically tuned phase shifter, which enables tuning of the frequency and locking. And of course, the crystal resonator, which has a Q of about 1.3 million. The measured phase noise of the oscillators built in this topology was about minus 123 dBc per hertz at 1 hertz and minus 148 dBc per hertz at 10 hertz. And those results were also presented at the European Frequency and Time Forum last month. This is a full circuit diagram of the crystal oscillator. This is the differential amplifier. You can see that we can take the output directly from the other arm of the amplifier without the use of an output coupler. The amplifier also offers non-saturated limiting, low flicker noise corner, noise matching, low noise figure, and precise control of the power delivered to the crystal. This is the spurious resonance rejection filter. which only is based on only 3 reactive components. The electronically tuned phase shifter uses varactor diodes and is based on a 5th order high pass Butterworth filter. And of course we have the Crystal Resonator. 2 oscillators were built with this topology. This picture shows the latest version of the oscillator package. Is a 6x4 centimeter aluminium enclosure which encloses all the oscillator electronics as well as the resonator. And we also have slots for temperature stabilization elements. But further optimization and miniaturization of this package is still underway. The measurement configuration that we used to measure reliably the phase noise of these crystal oscillators is actually we used 2 oscillators almost identical, one used as the external reference into the Symmetricom measurement system and one used as the input. This brings the noise floor of the instrument down and also helps avoid anti-correlation effects. And using this configuration, we were able to measure, well, this graph, by the way, is the combined phase noise of the 2 oscillators. So the actual phase noise of a single oscillator will be 3 dB, at least 3 dB better than this graph. And the measured results are about minus 122 dBc per hertz at 1 hertz offset and minus 147.7 at 10 hertz offset. Now for the dielectric resonator oscillators, this is the block diagram of the configuration. It's also a feedback oscillator configuration. Each one of these amplifier blocks contains 2 broadband feedback amplifiers in a push-pull configuration. 3 dB splitter was used as the output coupler. It was placed in between the 2 amplifiers in order to limit nonlinear saturation effects in the second amplifier. The resonator is a barium titanate part glued onto an alumina support, and we also have a phase shifter for achieving the correct phase shift for oscillation. One important thing to notice is that we measured the noise figure of the amplifier at the points where the whole loop connects to the resonator cavity. So in the measurement, everything was included from the both amplifiers, the output coupler, the phase shifter, and also all the cabling. This is quite important because when we plug the noise figure into the theoretical model, this will make it agree with the measurement better. So the broadband feedback amplifier uses an active bias controller to bias the transistor. Resistor R1 is used to set the collector current, R2 is used to set the gain of the amplifier, and R3 is used to set the input and output impedances to about 50 ohm. The resonator itself is, as I said, a barium titanate puck, and is glued onto an aluminum support, which in turn is glued onto an aluminium holding plate, which can be bolted inside the cavity. The resonance frequency was 1.49 gigahertz. This was intentional. It's 10 megahertz below the 1.5 gigahertz frequency because it's much easier to tune it up if we desire than to tune down the resonance frequency. Insertion loss of about minus 5.2 and loaded Q of about 19,600, which makes the unloaded Q about 43,270. This is a photo of the resonator inside the aluminium cavity. Printed probes were used for coupling the signals in and out of the cavity. And using all that, 2 oscillators, identical, were built and placed inside a metal screen box. They were powered by lead-acid batteries. And we also have some insulating foam to damp any vibrations that can degrade the measurement. Now, when measuring these oscillators, we couldn't just plug them straight into this Symmetricom system because the frequency is too high. The Symmetricom only measures up to 30 megahertz. And so what we had to do is we tuned the oscillation frequency of both oscillators so that they're spaced by about 2.2 megahertz. The tuning is achieved by these tuning screws on the lids of the cavities. Then we mixed the two frequencies to get a beat note at about 2.2 megahertz. We used low pass 1.9 megahertz filter in order to filter out the higher harmonics so that they're at least 30 dB lower than the fundamental beat note. The amplifier and attenuator were just used to bring the signal level to acceptable power for the symmetrical measurement system. This graph shows again the measured phase noise of the DRO. This shows the combined phase noise of the two oscillators again. And so an individual oscillator would have at least 3 dB better performance. And so at 100 hertz, we got a measurement of about minus 113 dBc per hertz, and at 1 kilohertz, minus 143 dBc per hertz. Now this is a comparison between the theoretical model, theoretical graph, which was generated using this equation right here. This equation is mainly a function of the ratio of loaded to unloaded Q, the noise figure of the amplifier, the flicker noise corner of the amplifier, and the power in the oscillator, which in this case is about, it's over 200 milliwatts. Also, the noise figure was measured to be about 11.5 dB, so there's a lot of room for improvement in that still. We can see that there is some divergence, although at medium offsets the theory agrees quite well with the measurement, or the measurement agrees quite well with the theory. At longer offsets we see a divergence, but this is mainly due to the measurement being limited by the noise floor of the instrument. So since the agreement is quite good in the medium offset range, then we can extrapolate that curve based on the theoretical model for higher offsets. The divergence at the lower frequencies is possibly mainly due to the fact that these oscillators were measured in a lab where only a few meters away people were slamming doors and walking around and things like that. So although we try to damp the vibrations, it's not ideal still. So this is a graph which compares the multiplied up phase noise of the Crystal Oscillator that was built at York, and the blue graph is the 1.5 gigahertz DRO phase noise. And as we can see, the Crystal Oscillator has much better phase noise at low offsets, while the DRO takes over at, or would take over in a phase locked loop at longer offsets. And that is what we plan to do in the future, is to actually complete the design of the phase locked loop and conduct measurements on the full local oscillator chain, continue miniaturizing and optimizing the DRO and the Crystal Oscillator designs, and eventually lock that local oscillator to a rubidium CPT physics package, which we have been developing from scratch, and it's gone through multiple iterations, each one making it more compact and more robust. But this is still, again, work which is ongoing. And in the end, I would like to thank CELXCS for providing my studentship, and also Mark Huff and Andy White from the University of York for helping with manufacturing most of the components for the physics package and the oscillators. Thank you.